framework of a collaboration within the so-called iThe collaboration on wireless sensory networks. And he'll be concentrating on neural-inspired information processing that we've been working on recently. And he will follow an approach based on FPGAs. So very welcome here. Please give him a hand if he needs anything from you. He's in the same cubicle as Nails. You'll find him there. So welcome.
Okay. So let's start. It's a pleasure to have here Joaquín Marro. He's professor, doctor. Not that I started. He has 2 doctorates. One from Barcelona. He was doctor as well. From Barcelona, from Universidad. He's actually one of the leaders in the field of non-equilibrium mechanics and has helped very much in creating this community in Spain. He is the founder of the Institute of Carlos Charles I for Computational and Critical Physics in Granada. And before, he was at Barcelona University for 15 years. For many years, he was a visitor at the Coherent Institute of Mathematical Sciences at New York and Rutgers University, where he had a collaboration, long time collaboration with the Boltzmann holder, John Lewis. You know, in mathematics, we have this Erdos number. I think in physics, we should have the Lewis number. Measuring our distance to collaboration with John Lewis. Joaquín Marro has a Lewis number 1 and number 2. Probably Lewis has as many papers and has collaborated with so many people as Erdos. So we should establish this number. He has been for a long time, 25 years now. He has organized this conference school in Granada about every time about a very interesting topic related to critical physics. Next year conference about physics meets the social sciences, emerging cooperative phenomena from bacterial to human group behavior, which probably also reflects his current interest. He has worked on several aspects of critical physics, including theory of transitions and critical phenomena, non-equilibrium steady state, lattice models, complex systems, stochastic processes, kinetic and master equations, etc. He has co-authored around 200 publications, and his earlier and some of his most well-known work includes the kinetics of phase transitions, mostly to the problem of phase separation in binary laws, where he combined the use of numerical work. He was one of the pioneers in using intensive numeric simulation to study the dynamics of phase separation alloys, and also theoretical concepts such as bringing this idea of dynamical scaling, which at the time was in other fields like in critical phenomena. He is well known for studies on non-equilibrium states in vivid different systems with competent temperatures, disorder systems, and many others. He has now is the advertising part, has a book on non-equilibrium phase transitions in lattice models with Ronald Digman, which is one of the key references in this area. More recently, he moved to study the hopping model for neural networks, especially the hopping between the different attractors and the size of the attractors. And most recently also, the influence of topology of the performance of a neural network. This is associative property, which we have from Miguel Antonio, according to his, so he told us some time ago. He's also a good communicator of science for general audiences. He was here before even a talk in this series of La Caixa conferences. We had one yesterday. He has published a book. First in Spanish, it was called Física Híbrida, and now it's been translated to English. I don't know if it's available already in English. It has already appeared in English by Springer. It's called Physics, Nature and Society, a Guide to Order and Complexity in Our World, which he exposes in a very clear manner for the general audience the basic concepts of complex systems. When I saw him some months ago, and he told me he was working on this idea that the brain is critical, I thought that, this idea, we are a little bit skeptical at IFISC about this. And they say, okay, I want to go there and give a talk about this. Well, this is the IFISC attitude. So Joaquín has the IFISC attitude. He'll show you now.
And last but not least, he was the PhD advisor of Raúl.
And a very good old friend. Yeah, okay, thank you very much to Raúl and also to Maxi, of course. Let me introduce the group in Granada. This is a small group, but all there understand very well Spanish. It's a condition. So usually we have the seminars in Spanish. Okay, I come here to talk about complexity, and I have threefold motivation for do that. The first one is that I'm going to present you a new book on complexity at the very end of the talk, but this is not the important one. The important one is the one Raúl mentioned, that I want to lack of control. I like to convince you that the concept of phase transitions today is very, very relevant to understand brain structure and some of its functions. But in addition to this, and complexity is a good context in which I can introduce you this idea. But in addition to these two motivations, there is a third one, which is also important. And I feel it's important here in this context where most of you have an idea, more or less clear, of what complexity is, more than in other audiences. But I'm sure that if we contrast our opinions on this concept, we will not agree on just a definition of a complex system. And I wonder if you eventually ask yourself if a given system was complex or not, or even if a given system was very complex or just slightly complex. So there is enough reason to talk about complexity. And in fact, there is a problem, because if you put complexity in Google, you will get these images which have nothing to do with what we physicists believe about the topic. And in the same page, perhaps, or the next page, you will find that an engineer says that the Boeing 777 is a paradigm of complex systems because it consists of 3 million parts flying in close formation. and in the next page, you will find another engineer that says no. The reason is that it consists of, it involves 4 million lines of code. Probably you have heard seminaries or conferences about complexity by computer scientists and mathematicians, and probably you feel that their understanding the use of this concept has nothing to do with what is around here, biocomplexity, complex systems, and so on. So, okay, in the same, I was invited 1 year ago to a meeting in which I found 30 philosophers and sociologists, real sociologists, no like myself. And the meeting was precisely to speak about complexity. It's very funny, probably the book is in your library. It's very funny to have a look to that because, well, as you can imagine, everyone said things completely different. I was the only scientist, let's say, and all of them cited very much me in my book and so on, but almost 2 years ago there was of nature, and at the beginning of it, this game said this thing: formal definition is not easy. Even it's not clear who should care about this concept. He means, I understand, who should study that: physicists, biologists, engineers, mathematicians. So this is I think is corrupted, because first, in the ordinary language there is a meaning for complexity, and then it's very attractive. I think it's worth to speak a little bit about it. Let's go to complexity in physics from my point of view. Probably all of you, or most of you, will agree that this is an example of complexity. But why? Because, okay, we don't care if this is a dangerous accident or not. And we know to understand how this orbit was built. We know that it comes from the sense, another current, a gradient, a temperature gradient, a humidity gradient, a convection, and so on. But we physicists know that the origin of this is in the movement of molecules in some force fields, and we are unable to topology to that origin. And the challenge is even more important if we go up and see this from above, which looks like this, and then we realize that the same kind of phenomenology happens in some galaxies. And we know that this is a logarithmic or a Fibonacci spiral, but how is it possible that such close phenomenologies can occur at such distance scales? Okay, but this is not the only case in which we physicists have a great challenge. I collected here some examples of the same kind of challenge. My videos, for some reason, didn't understand, are not working. So this, imagine here birds flying and fishes avoiding the predators. The fact is that here we have similar challenges. Some of them come from turbulence in many different contexts. The financial markets, the trend, the gravitational fields, the colonies of batteries, and so on and so on. Here you have all processes, and these problems, we every one of them with a complexity. For me, complexity is the common divisor of all these phenomenologies, including other examples which are similar to the ones here. So let me try to pick a few observations from these phenomenologies, but I'm going to take the examples from our study in Granada concerning the brain, so that I can conclude that the brain has much to do with the concept, the physical concept of phase transition. Okay, my first observation, it's a very simple one, all of them are very simple, that complex systems are out of equilibrium. Okay? We know equilibrium states, you may define them as a maximum of entropy, and we know they are stationary. And thermodynamics says that they are homogeneous also and history independent. And statistical physics says that they are characterized by a well-defined Hamiltonian, because you need to be able to write a Gibbs probability of that sort. Okay, that's not the case for complex systems. It was observed 2,500 years ago that everything is changed. Okay, second observation. Technology which interests us is nonlinear. There are many linear cases. Law, perfect crystal, normal modes, Fourier, etc. To harmonic approximations like thermodynamics. The real work is not the sense, for instance, that the superposition principle does not apply to the systems in which we are interested in. So linearity and thermodynamic equilibrium is not a property, is, let's say, an anti-property of complex systems. Let's see a case in which precisely non-linearity and non-equilibrium causes the relevant phenomenology. And the case is a simple one. It's the case in which a signal is transmitting but usually while they propagate, as it waves when you throw something to a but you also know that in some cases they may even get reinforced while traveling, and then that medium is excitable. And a book example of that is the propagation of flames in a forest fire, in which case, in spite of great irregularities, etc., the fire will last as far as there is forest or firemen are able to control it. Well, this is not the only example of an excitable medium. Probably you know many more than I do. But for instance, the muscles, the electric activity in the living beings, and also to be a condensed matter physicist, reaction diffusion processes. There are examples of propagation forces in those conditions. What's the mechanism which makes this possible is a very simple one. An element, the 3, for instance, in the book example, which you can think of it as a node in a network, becomes excited for some reason, then it excites neighbors, and then relaxes for a while, but the neighbors excite their neighbors, and so on and so on. This is clear that impedes both linearity and non-equilibrium. It's impossible any of those conditions under this mechanism, under this microscopic mechanism. Let's ask ourselves: has the brain this feature? Well, there is an interesting experiment by some Japanese people, which consists essentially in you put a friend in a chair and you breathe air on the eye. What you have built a machine which throws the air, but also is able to measure the blinking which is induced by the air breaths. Okay, the air breath are supposed, you interpret that as an input which propagates through some neurons, and then those neurons react to that signal by the blanking. But you put the same person some headphones with noise, just noise, and you tune the level of that noise. So it's quite intuitive that eventually you won't be able to synchronize input with output. And so these people compute the input-output correlation as a function of the noise level and found those numbers. I don't know why didn't found more numbers, because the experiment seems easy, but probably it's not so easy. The case is that you can plot that in a semi-locally plot like this one, and it looks that way. And we try to interpret these numbers, and we did the simplest things you can do is to assume that the neurons which are involved in the experiment can be described by this simple equation by a voltage which is changed with time according to this equation, and then you can make assumptions on this function, which means assume different types of neurons, and you can also make assumptions on the synapses, on the relations between the neurons, the different neurons, and the result of that study can be summarized with the table, with this table, and we see that in two cases we have two maxima, only in two cases out of the 6, and then it seems that those data could be interpreted in that way. So it happens that these cases correspond more or less to the same situation, which can be described as neurons of a type which is called fixed cube Nagumo, which are characterized for being fully nonlinear and to have a dynamic threshold. And synapses, in this case, are assumed to be a short-time dynamic, to have a short-time dynamic which is observed in practice, so is appealing to make that assumption. Okay, then we are able, with that simple assumption, to describe well the data. Okay, this is rather familiar in many different fields of study, and is called stochastic resonances. In this case, multi-stochastic, multi-resonances, because there are more than one people.
Okay.
Yeah.
With the same figure, you can fit a straight line, a constant value for the frequencies, and just a single peak, because the error bars are big enough that permit.
Yes, that's true. But what's the theory which explains that?
Which I normally stochastic.
That the guy just did and nothing happens.
No, because I think for low frequency the system does not equally respond to the different.
You're right that that's not. I like to have, and in fact, I'm trying to push people to make this kind of experiments, which would be very, very interesting, and they seem simple. But I have behind this, as you see.
The symbols are also numerics.
Pardon me?
The white symbols are also numerics.
No, this is a different thing. Okay, so it's just making different assumptions on the model. You find that kind of behavior. Different, which are assumptions more complex than these ones. Okay, so the fact is first that we obtain that kind of. It seems that this simple model and perhaps the data have that kind of stochastic resonance, one conclusion, and the other is that you have nonlinearity and you don't have equilibrium, okay? Which is my point. Okay, so, okay, we said, okay, let's make a better model of this situation. let's try with a complex network in which interactions have some of the qualities that you observe in neuroscience, and found behavior with qualitative behavior, which also okay, but well, also but is also more versatile, and you can symmetries play a role and things like that. The fact that those in back phase transitions, as in a way. So, observation number 3. What we could call the more is different scheme holds in this case. That means, you know that Anderson in Nature, I think, was...
Science.
Pardon me?
Science.
Science in 1972, but Bofman 1 century before that, and many others between Bofman and Anderson, more or less said what I'm summarizing here, that nature shows up as if there were various levels, for instance, micro, nano, meso, macro, which are organized in a kind of hierarchy, and each is well defined in the sense that each has a typical length, scale for length, time, and energy, and also each of those levels has its emergent properties and even specific theories, thermodynamics, hydrodynamics, and so on. So a consequence of this is, as you know very well, that knowing the basic elements and the properties, how they interact, for instance, is not enough to characterize the global properties of the whole system. And why? Well, the reason is that today is very clear, is that the elements interact non-linearly, strongly non-linearly, and that induces order, induces structure, induces even new laws, which were not present in the level before the one you are now studying, so that as people like to say in the case of this system, that the future cannot be predicted. At least you cannot make specific predictions, but just the statistical ones. Okay, well, two colleagues, Albert Barabasi said some months ago, the more we know about the working of genes, bands, or neurons, the less we understand the system as a whole. That's true. But even Feynman already remarked the fact that our minds may not understand implication of our equations. It probably he meant the same kind of thing. Okay, so let's make ourselves this question. How may we try to understand the properties which you observe concerning the human cortex by following this scheme, this more is different scheme? Well, it was already known in the 19th century that the human cortex has many different areas, and today those areas are rather well described, and you can say, you can define the cortex in this way. It's a mosaic with hundreds of pieces. Each of them is has the structure of a network. The pieces are very much different from each other, but strongly interconnected also. To have a clear picture of that, each has around 40 centimeters when you stretch the human cortex. I mean, you have some 7 by 7 centimeters as the mean for the surface of those pieces, and each has hundreds of millions of nerve cells. They count the total of nerve cells, and there are million in total in the human brain. They are strongly interconnected, a mean between 1 and 10,000 synapses per neuron. The coordination looks very smooth when you look the images from different experiments, but there are signals traveling at very high speed. So here we have network, what today is called a complex, a strongly dynamic nature, and this is designed by evolution to optimize cooperation, the cooperation among units. But how this cooperation is achieved in practice, well, the idea goes back to Santiago Ramón y Cajal 1 century ago, but to that today we can add an unusual mixture of different scientists. The most important ones, but probably you would also add a few more. And they gave us what we call in this context the standard model, which is something in principle very simple, that all of you assume that the neurons are characterized by some activities which can be represented by a variable, which in practice many times is sufficient to assume that the variables are binary ones, and by synapses, find the notation by synapses which have weights which are specific connection. So one defines a signal in each neuron, which is the weighted sum of the activities of all the neurons which are of neuron J which are connected with the Y1 you are considering, and then you change the activities of the system according to a probability which depends on the difference between that signal and some characteristic of the neuron you are considering. Then you inspire yourself in biology to make assumptions on the parameters in the model, the weights, the beta, the thresholds, etc. And then you put that on a computer and run. But still you need, because a characteristic of the brain is that it's able to store information. So how does this virtual brain store information? Well, following an idea which is also first in Cajal, but it was developed almost explicitly by Hebb, which is a very simple one. It consists in just storing different patterns as a combination of this kind, which determines the value of weights. Okay? Once you have this virtual system brain with those patterns memorized on it, these patterns you perturb it strongly as an initial condition to the system, and in some cases very well and very rapidly to the so this system, which is so simple, is not trivial at all. It's something which does efficiently, but that when I go to my home village, who is completely I have in my brain, I'm able to recognize him. But the machines are unable to do it. You have to so this perfectly, if you think, if you go back, this perfectly illustrates the scheme more is different. So you need to go through and connect levels. Otherwise, to know, in this case, neurons and how they interact, you need to work out that. We would then understand nothing about the brain or the complex system, whichever it is. It follows those organization principles that in which you are interested in. Another characteristic here, which follows here, is that you need computers, because even this model, the standard model, which is the simplest one you can think of to have this kind of functioning, even this one, the maths is completely impossible on it. So you need computers. That's why what we could call the creative use of computers in science is today so efficient in opening new paths of study. But you see that what I'm doing here is trying to convince you that we should consider the brain as a physical system. It was not a few years ago, or 1 or 2 decades ago. To be able to work with the brain as a physical system, to apply our techniques to the brain, we need data. It's what to make any sensible step. So you need data. And the fact is that these videos are supposed to be running, and they are very, very interesting what happens there, but there is, I don't know what problem. So the fact is that we have today lots of data, and the data concerning neuroscience is easily accessible, very easily accessible through friends or even sometimes in the internet, as I'll show you an example later. So once a physicist has data, is able to make models. And for instance, lattice models, because it seems is convenient in this case. And not only you deep on the understanding of a specific problem, the brain or a function, a specific function or whatever, but usually when you do that, as it happens in other parts of physics, you are able to uncover common properties of different systems. So in this way, here it also came an idea which is very familiar in physics, which is that of universality, what Feynman's like to call the principle, the parsimony principle, which is something like there are not so many different phenomena in nature, which is very helpful, non-rigorous assumption that which has basis for a century to develop arguments based in analogy. This strategy can be okay. My fifth observation is that there are two concepts which are very relevant within this context. One comes from mathematics, and is that of graph, of network, and the other comes from statistical physics, and is non-equilibrium, the concept of non-equilibrium phase transition. For instance, speaking about complexity, Barabasi also mentioned that a new discipline, he says the role which was played by the card makers and oil producers now is made by the companies which are devoted to the network science business. Vespiniani, on the other hand, said a few months ago that how the concept of non-equilibrium phase transition is relevant within this context. Okay, sixth and last observation, the phenomena which interest us has no scale. Okay? There is a scale invariance. As a consequence, the renormalization group formalism, which is able to describe that situation with lack of scale, and you know, probably it's a set of differential equations which have been very useful in studying critical phenomena, happens to be also interesting within this context to study the brain, because there is a mathematical structure which is in practice useful together with the theory of stochastic processes, of course. For instance, Anderson, reviewing recently a book of Sokals, says this in this way: I was delighted to find the renormalization group view of the world, which is an interesting way of saying that, according to which one sees every level of the hierarchical structure of science as an effective theory valid at a particular scale and for particular kinds of phenomena, but never in contradiction with lower level laws. That's certainly an interesting property of complex phenomena. Okay, we go back to this transparency. That model, the simplest version of the model, was able to recognize, but of course the brain does much than just recognizing. And what is missing that model is the network topology. You need to attack the problem of the topology of your network. Exactly how is that, how the neurons are connected. And a way to study that is to define the degree of a network, you know, the number of links each node has. There you have an example. And then it is observed that the distribution of the degree is not Gaussian, but is power law. And there is, as you probably know, there is an explanation for that, which is called the principle of linear preferential attachment. Okay, but we work out a little bit more and set up a model in which the preferential attachment needs not to be linear, and we found that in that case the structure presents a topological phase transition with power law solutions and also scale-free solutions. The model is very simple. It consists in assuming that the probability for attachment or the detachment factorizes in two terms. One is a local term, which you assume is a function of the node degree, and the other, well, there is motivation, you can think, but depending exactly on the phenomenon you are studying, and a global term which is a function of the mean network degree, which I'm writing as cat. Okay, you can also think of motivation for this global dependence, of course. Okay, then let's assume that you have a system and nodes with some degrees, and initially you have a distribution of degrees with some mean, and then at every step you have these dynamics. Each node gains an edge to a random node and loses randomly chosen edge with probabilities which factorize according to what Arias said. And you write this. Here, these are arbitrary functions in principle, and you can write down for large n a master equation, so you can study the dynamics of this model, and you can also study, of course, the stationary state. And okay, so we study several versions of this model. If we assume that the probabilities U and D are, which are the global ones, are the simplest structure, then it follows even intuitively to make the connected nodes, that is, those nodes with of k of degree have higher probability of gaining than of losing edges. The degrees of these nodes will grow, so the tendency will be to a heterogeneous network, while if on the contrary lose more edges than they gain, the tendency will be to homogeneity. And the fact is that the topological phase transition separates those two regimes with a critical point, a well-defined critical point. Okay, so we apply this to the case of synaptic planning. You know that after a violent stage of unsynaptic genesis, there is a process in which there is occurs some planning in the brain, and it's okay for me. I don't know if you can see it. And there are data concerning this process by there are several ways of getting data, and there are even videos, nice videos which describe this process, the genesis and also the planning. Well, the qualitative situation is more or less than this one, that after that rapid increase of the density of synapses per neuron, then it comes the planning. And that planning is made with certain criteria which are not well known. Probably are important the search for economy of energy, because the brain consumes a lot of energy as compared to the rest of the body, and also probably to make more efficient the coefficient, the connections. The fact is that it is assumed today that there might be different types of planning, and that the type of planning would determine the intelligence of the person in question. And also it is assumed today that anomalies to this kind of types of planning would correspond to autism, in this one of the case of intellectual deficit, and in the case of a gifted individual, to the schizophrenia would be also an anomaly of of that planning. And also, well, in fact, there are studies going on which probably in not much time will make this assumption true. And also it's interesting to mention that probably that loss of early memory we have, that we don't remember as a general rule what happened in our 7 years of life or something like that, probably has to do precisely with this fact, the fact that many synapses have been suppressed after 7 years, and the memories are indeed printed in those synapses. Well, the fact is that we can adapt our model to try to describe data. Okay, with the simplest assumption, we obtain this kind of behavior. We have added here exponential initial growth to the behavior of our model. And well, you see that we have two fitting parameters, but are natural ones, so that you can check that at least the order of magnitude is correct. And the fact is that we are able to describe data. The most, so far, the most complete data corresponding to this phenomena. Okay, today there are very important data concerning these interactions. There are, as you probably read in the press, that there are today you can obtain from your friends a matrix, the matrix of connections corresponding to the human brain, not yet at the synaptic level, but averaging many thousand synapses, of the order of 1,000 synapses. And it has this, well, there are many different images which are available in the internet, and those connections have this, they even know the direction of each of these connections, which correspond to what is a different story. And more recently, even there is a project in the Paul Allen Institute which concerns the mouse, which is very important because the brain of the mouse is very close to the human one, and this is, they are already close to the synaptic precision, accuracy. So we are about to have, as I said before, we are about to have very good data to try different hypothesis models under different hypotheses. Well, the fact is that we took the same model as I described to you. If we define, okay, if the local probability pi has this behavior, so we put a power law there as a definition of the model. And if you define this parameter, which you see is this is the variance, is a minus signal, and this is the mean. So when this m goes to 1, you have a homogeneous situation, while when this goes to 0, you have a heterogeneous situation. And then we find this kind of behavior as we change the value of alpha. Okay, so there is also a very well-defined transition between two regimes. One is homogeneous and the other is heterogeneous one. Okay, we check with the case of the C elegans, which is the simplest check one can do, because the C elegans has only 300 neurons, and the data is available on the internet. But well, the fact is that we are able to describe very well the data concerning this worm, and that it happens to correspond precisely to the critical condition in our model. Okay, Well, here there is a conclusion which I think is important because it's intriguing. It is suggested by the behavior of this model, of this simple model, that a network which is subject to an optimization mechanism, and we are thinking, of course, of the natural selection, evolved to appropriate the structure by tuning microscopic actions. So that if the being in the critical region for the system, it seems that making some adjustments at the towards that structure. The model also shows that simple dynamics is able to produce a structure which can be homogeneous or either heterogeneous or even scale-free at the critical point. And in fact, there are many indications today concerning criticality in the brain. At least one of them in this list, which is rather arbitrary, corresponds to people, I don't know if here, but sometimes it's in this room. But constantly are now appearing papers in the most important journals which claim to observe criticality and phase transitions in the brain. But I find two problems to understand this whole set of papers. The first problem, the critical region in the observations concerning the brain is broader than the one which is familiar from condensed matter, where usually we have a point, a critical point. Here you have a region in which the things go critical. So what's happening? Well, the hypothesis was in some moment that it's likely that simply this is a consequence of the system to be out of equilibrium and therefore to be characterized by a great heterogeneity. So that makes that it's much more simpler than in equilibrium, that many scales sum up and give, in what they make is to make broader the critical region. Okay, so you can illustrate this would be the usual situation in condensed matter, while here it appears something which some people call Griffith spaces, which remind the critical point, but in a large, rather large, broader region. Well, where we have two proofs that this could be the case. One comes from some experiments, numerical experiments of the magnetization of magnetic particles, in which we observe clearly that due to some great heterogeneity in those cases, there is a sum of scales, and there is an apparent critical behavior which holds very rather generally. And the other is something similar also in the group, showing explicitly that there might be Griffith's phases, what is called Griffith's phases, as a consequence of non-equilibrium phenomena. Okay, but what in the brain? This concerns simple models. What in the brain? Well, as probably Miguel Ángel Muñoz already told you, they were able to show, using the matrix of interactions provided to them by the connectoma, human connectoma project, they were able to show that this is the case concerning that situation, that specific situation. Okay. So chances are that this, my first problem has can be understood in the near future. And the second problem I have is who tunes here the parameters corresponding to pressure and temperature in condensed matter. Okay, to understand this, we need to make complex the interactions in the standard models. And let me show you the simplest case one can imagine in which interesting behavior follows. Assume that the fields that arrive to a neuron, instead of being as according to the Hertz rule, you put here an x, which is a stochastic variable, which has some distribution, for instance, the bimodal one, in which this probability, this is the probability that you see the synapses, this specific synapses takes a value given, which is a parameter of the model, okay? And you take this depending on the order of the system at that particular moment. Okay, you can work out this idea in several ways, of course. If you want, we can discuss that later. But more or less, different ways we establish led to the same situation. And so the important thing is that we have a parameter here which has as model parameter, and you have beta, which is controls how is the dynamics, how random is the dynamics of your system. You have also a noise parameter. You see that if you make this noise parameter equal 1, you recover the standard model. But if it is smaller than 1, is as if the synapses has fatigue, has been described, and if larger than 1, as it would facilitate the transmission. And in addition to that, we are adding a parameter which happens to be very interesting, which is the fraction of active or synchronized units, neurons, in your case. For simplicity, you may assume this, and it happens exactly the same, that you choose at random that fraction of, but you can also think of more complex situations. The fact is that this mimics excitability, because that's what excitability does, is just to maintain some of your units in not active at each particular time. But also is interesting in this context because it mimics persistence of memory. It seems that sometimes some neurons stay in their actual state to give that information to the neurons that have adopted the next state. Okay, it has been described in that way. Okay, let me refer to the case of fully connected neurons for the moment. Okay, just to simplify and just to focus on these news facts. Okay, the situation we find out is this one. This is the phase diagram as you change the noise parameter and this row parameter, this excitability parameter. And the fact is that especially in this region you find very, very interesting behavior, which includes these three types, different types of behavior, in which in the three of them there is a constant visit of the global activity of the system to the different attractors which the system has, corresponding to the patterns you have stored there. Okay, but you see that the visits are very irregular, and it happens that for some values of the parameter, the system visits only those patterns that are very correlated between them, while if you change the parameter values, you can make the system to visit also patterns that are not so much correlated with the one in which the activity is. So, in the simplest versions of the system, you can demonstrate that this irregularity is chaos, is mathematical chaos. So, in unidimensional cases, Lyapunov exponents which are positive, for instance. Okay, so it seems that due to chaos or to some very strong irregularity, the system is able to be in a kind of a state of attention, because even if you are interested in some information, you eventually check the other points of interest. Well, this kind of behavior also has been shown to be from in an independent study by Miguel Ángel Muñoz y Jesús Cortés, also from the group. Well, so it follows 3 or 4 interesting things here. First, that those mysterious stochastic resonances, now with this model you can observe that precisely correspond to the transitions when you move towards the most interesting regions. So are just phase transitions, nothing more than phase transition. And then the model also mimics other aspects of reality. For instance, you observe, you measure long-range correlation. These are some already in many different instances corresponding to the brain. And also trajectories as in the model have been observed experimentally, and an outstanding case is that of those studies of oral processing, for instance by Masor and Loren in 2005, and also by others after that, in which they observed that the global activity of the neurons which are connected to the antenna of the insect have shown this kind of a chaotic behavior. They describe it as chaotic flow. They don't demonstrate that's mathematical chaos. Okay, we are able to recreate with our system precisely that kind of observation. So a conclusion here could be that that instability which is inherent to, which characterizes the chaotic motion, seems to facilitate moving the activity to any memory at any time, as would occur in a state of attention in the human brain. This is could be almost summing up the other observations, that criticality, to me at least, in this context, reminds that edge of chaos hypothesis. You remember 25 years ago, Lanton and others said more or less that biological systems can perform complex computations only by operating at the borderline between a chaotic phase and an ordered phase. Okay, so I would rephrase that, and I'd say competition among different memories may cause quite irregular, perhaps chaotic dynamics that under non-equilibrium conditions may bring the brain and other systems as well to rather broad critical regions where intriguing complex behavior shows up. So it can be summarized in this way, that we have an area, a rather broad area, where is criticality, there is complexity also there, And the other parameter here, what would be? To me would be complexity of the synaptic networks. And there I include topology and also time variation, which seem to be first real because occur also very important in the models to obtain the most interesting behavior. And what is then a complex system from the above? Well, I would say, and it would be my almost definition, it would say a set with many elements which are equal or very, which shows hierarchically organized and well-differentiated levels of description. You need to relate those levels of description, because knowing the elements and the relations is not enough to understand what emerges from there. And also the set is characterized by intriguing phenomenology, and this includes, as the most important one, nonequilibrium, universality, criticality, and scale invariance. And as a consequence, there are useful concepts, two useful concepts to me. One is network, which is the correct way of describing cooperation, and the other is phase transition, non-equilibrium phase transition, which is the correct way of describing, in this context, order. And also it follows that the useful mathematics here are, in my opinion, two. One is the theory of stochastic processes, and the other is the renormalization group formalism. And a reference to my talk would be this from my own. First, the book, both have been mentioned by Raúl. This one describes the techniques, the mathematical physics techniques to study non-equilibrium phase transition. And this one is a new one, which is at a more divulgative level, but thought for physicists. In fact, my friends, physicians, for instance, don't understand it. So it's I insist it's for physicists. But the point is here, which could be interesting to you and debated by many of you, is that there is a kind of a formalism which is appearing, which affects many systems in physics, but also in biology and also in sociology. And this common scheme, which is not yet very, very well defined at all, has to do with complexity, and has to do, as I think it stems from my talk, with the non-equilibrium statistical physics to be developed. Okay, thank you very much.
Questions?
Yep.
In the last part of your presentation, you introduced this chaotic itinerancy process in the last model, where you see the chaotic itinerance between different attractor ghosts. And there's two aspects that I do not fully understand about that. First is, how does this relate to critical behavior? Because I guess this is supposed to model the rest state that, for example, your solver is in. And the second, you noted that this would allow the search process a certain memory arbitrarily fast from every position. But that would require that in this heteroclinic network, every attractor ghost would be connected to any other, right? And how far are those aspects?
Let's go with the second one, which is very interesting. Your comment is, I am close to be able to demonstrate, but not yet, but I'm sure it will come mathematically, I mean, that there is, you can define a probability transition from one attractor to other. And that probability transition depends on the model parameters. I'm working on the simplest model, it can be, of course. And, but depends also on the difference measured in some sense between the two attractors. And that's very interesting because that means that probably those things we observe numerically, what is happening there is that indeed there are different kinds of behavior. For some model parameters, you only visit those patterns which are very close to the phase in which you are at that moment. While for other parameter values, you are able to go far away from that phase. Okay? So, but in any case, that is very irregular. Is very irregular. You can monitor, for instance, the times the global activity stays around a given attractor, then moves to other. You can see how the probability of times of elapsed times is, and you find, and I go to the first question, and you find long range correlations. So that's what I mean, because I agree that the description I made is still rather a bit confused, because I'm thinking about a structure and I'm thinking about function. So concerning a structure, is rather clear that sometimes our models adapt to the critical region. But when you have dynamics, it's not so clear. But the fact is that the real systems would have both. Would have topology, perhaps critical topology, besides this kind of irregularities, which come from competition between attractors and so on. So that's a mess, which it will take a long time to understand the details. But that's my feeling, no? That there is kind of criticality in a loose sense, both affecting structure and dynamics.
When you mentioned the structure of the network at the beginning, I understood it was a topological effect when you measure the number of links that you have in each node. But certainly that's not relevant, because what is relevant is the node is active or not.
Yes.
So how do you count for that in the model? I know that you give some weight and so on, but
yeah.
you are dynamic.
Yes, but again, I'm in the model you refer to, I'm just drawing lines, not speaking about weights of those lines. You see? So, yes, the one which describes the stationary network of the worm is just lines. We are just counting lines. Okay?
Yeah,
but of course,
view needs to be active then, because
yeah.
it might be there, anatomically it might be there, but if it is not active,
yeah,
it doesn't care.
Yeah. Well, as you know, some of these, I think most of these matrix interactions concern active, not active at that moment. Okay.
So, thanks Joaquín for the talk.
Yeah.
I more or less agree with everything that you have told us, but I disagree in one point. For you, the network, the concept of network is fundamental for complex systems. And maybe just for the brain, but for me, most of natural complex systems, networks not necessarily appears. You have something for
yeah, well, yes, you're right. For me, a network is just a tool to describe cooperation. The important fact is that you have units cooperating there. But whether, for instance, as Claudio says, whether there is a physical line, or I mean, you can have a physical line, but if the physical line is not active, there is not a connection. So the concept of network again is just a tool.
But do you think it's a good tool for any?
It's a good tool. In this moment, I think you need that tool.
But I agree that it's useful for the brain, but I don't think it's useful for the atmosphere. I don't think it's useful for the ocean.
Oh well, but there are many. It's useful in condensed matter. It's useful in genetic problems. It's useful in many different places. I don't know in nature. In nature, I don't think studies are at this level at all yet. Maybe they will be in the future. I don't know. You see, maybe if you connect by means of a network different local systems, I don't know. Maybe, I don't know.
Another comment on. We talk about this face recognition problem, where you give the machine which is distorted, then it might or might not reach the correct one. And you think, okay, the brain can do it much better. I wonder what is this situation that happens with the chess problems of years ago. They say, oh, the machine will never beat the man. The man can always be better at analyzing a position, see the different frames, what will happen. Nowadays, any computer will beat your chess, absolutely. So I wonder whether it's just a question of getting the right algorithm to do it. Whether we are far from a machine actually being better than a human being in recognizing patterns, distorted patterns. I mean, my feeling is that all you need is a good algorithm. For instance, I'm sure for fingerprint recognition, it's better the visual.
No, but you see, we are able, with this kind of models, we are able to make fingerprint recognition. But
better than a human, probably.
Yeah, better than, yes, and better than those. You know that the usual algorithm for that it does not work this way, but they have some theory that the prints are, I don't know the theory, but so they just are based on that theory. Not here is kind of comparing correlations, global and local correlations in some complicated way, which are able, which patterns are stored is a very simple one. It's just a superposition of the patterns in the brain, and but that's very effective later in recognizing in a particular state whether you have some of those correlations. So it's very tricky. It's very interesting. This standard model, which seems so simple and has been known for so many years, I think it's very interesting as a starting point.
Pattern recognition problems.
Yeah.
I think there's no general limitation, but it's the question I think I would extend it from your point is not whether you can do it better than a man, but whether you can do it as efficient. Which can, for example, how many servers of Google do you involve? So can you do it with an amount of energy consumption which is equivalent to the brain? Can you do it as efficient as the brain? And I find even a more interesting question than whether you can do better play chess.
Okay.
I have a question.
What's the result?
No one asked me.
That's right.
So, can you measure how complex a system is? Are you interested in that?
Oh yeah.
Well, I think you should not be interested in that. But there are many people studying that. They're saying that who cares whether a system is very far from equilibrium or not very far? Of course, you can make assumptions about local equilibrium, which are can be useful to, or you can say this system is almost linear. the superposition principle almost holds, but this is a different thing. A complex system needs to be non-equilibrium, non-linear, so it's not interesting to know whether it's far from non-complex or not. No? That's what I think. But this is, okay, it's something that perhaps, that's why I mentioned it, perhaps you have a quite different point of view, because there are many people, well, many people, there are some people working, especially mathematicians.
Okay, we can continue.